Okay, I'll just give everyone a few minutes to join. Okay, I think everyone's joined. Good afternoon, everyone, and welcome to another IET Humber lecture. This is part of our lunchtime series, and it's the third one in total of the series so far. So welcome. The IET Humber, for those that don't know, is based on the east coast of the UK, and our members are both on the north bank and the south bank of the River Humber. The lecture this afternoon will be from Nick Thompson of Schneider. Nick is the HV Training and Marketing Manager for Schneider, and the topic this afternoon will be the basic principles of protection and a brief introduction to IEC61850. Okay, a few points for housekeeping before we start. The slides will be available afterwards. They'll be put into a PDF, which can be distributed as required, so they will be available. For those that need a CPD sheet or certificate, I will copy the link for the CPD into the chat box at the bottom. I've also been asked by the IET to copy a diversity survey, and that'll be also in the chat box at the bottom. So if you could take a few minutes and have a look at that and complete it as well, please. Also, as we normally cover sort of the local area in the UK, but we do realise that people from all around the country and sometimes the world do join in these presentations. So if you could put a brief comment in the chat box, kind of where you're from and how you found out about the event, that would be great. Thank you. Finally, questions. What we're going to do is keep all the questions until the end. And then if you could put those in there's a box at the bottom, Q and A. So if you could put those into that section, I will read them out at the end, and Nick will provide the answers for you. The lecture this afternoon will take around about 50 minutes, and there will be time at the end to go through the questions. Any questions that we can't answer during that time, I'm sure Nick will do his best to answer afterwards. So without further ado, I'll hand over to Nick, who will take us through the presentation. Thank you.
Right, thank you, Andrew, and thank you very much indeed for this opportunity to be able to speak to you all this afternoon. And a very warm welcome from myself. I'm based at the Leeds facility, which is our factory for manufacturing high voltage switchgear. Schneider does actually refer to the voltage range that the switchgear is used on as medium voltage, but in accordance with the 18th edition, which is a UK thing, I shall refer to it as high voltage for today. So today's subject is all about HV protection. It's an introduction, and before we swing into the presentation, just a little bit about myself. I am based in Leeds, which is in Yorkshire. Now, Andrew's already mentioned the Humber. If you draw a straight line across the country from the Humber to the other side of the country, about halfway across is the Pennines, and just to the right of that line on the Pennines is Huddersfield, is where I live, and then Leeds is just a little bit further to the right. Is where the factory is based. Now, the products that come out of that factory do go all over the world, but they don't go into Europe because the voltages are too high for the equipment. However, that's myself on the screen. Been with Schneider Electric since 2004. I've got a few interests. One of them is running incredibly long distances, but that's for another day. So just briefly, these are the subjects. I've broken the presentation down into these workable and bite-sized chunks. The presentation itself will last somewhere between 50 and 55 minutes, depending on if I get distracted on any of the subjects there. But I've tried to take you through a story introducing you into protection. Now, the concept of protection is all about protecting the assets, protecting people. Okay, so as engineers, as consultants designing systems, we need to build in a series of weak links. Now, mechanically, you'll have all have heard of the term, it's only as strong as the weakest link, and that's very certain in the electrical circuits. So we don't want things to go badly wrong, and things do go badly wrong, and we hope that the protection that we've designed into it will be adequate to stop anything serious from occurring. So that weak link is going to be a series of weak links, and certainly with high voltage protection, we work on an upward chain. So if the one at the bottom where it's meant to work doesn't, then we're hopefully relying on the one above it to work, and so on until one does actually work. Now, there is concepts called the proverbial 6-inch nail, which I came across when I was an apprentice back in 1975. But more recently, people have been a little bit more creative by using a screwdriver, as we can see there. They pull these from the good old World Wide Web, and somebody within the IET has done a little bit more of a closer study as to other things that you may find. So spanners, bolts, nails, screws, ring pulls, even the cream cheese in the triangles. Laughing Cow is that one there, but unusually a bullet, and that's the one that caught my eye. That's the audio visual alert, as well as blowing it at 350 amps. Now, the thing is with fuses, which we're all familiar with on the 13 amp plug, which is we use in the UK, it has a small piece of wire in that fuse. Now, that fuse wire will heat up when it reaches 13 amps. It won't blow straight away, but after a period of time, that fuse will actually break because of the high temperatures within it. So, why are we concerned about electrical faults? Where we've got heating effect. I²T is the most common one, and any potential joints within the electrical circuit, and these are bolted joints, soldered joints, welded joints, whatever, if they're not done correctly, are going to be potentially very high hotspots. And if you leave those hotspots running for any period of time, then you're going to get potential problems with a wider area. Now, what you don't appreciate is stresses on switchgear cables and such like. This is a video I've pulled from YouTube, and unfortunately I can't attribute it to anybody, but it's been filmed in the lab, slow motion, so high-speed camera. And this is low voltage cables which have been subjected to extremely high voltages and extremely high currents that passing through it. So what appeared to be nice rigid cables at the beginning, they've turned to what I refer to as plasticine, and you can see the whole infrastructure there is now waggling around, and I liken that to cables wagging. So you wouldn't want those to start flapping around like you would have with a hose pipe when you turn the water on, and you haven't turned the hose pipe off at the end. It starts wagging around all over the place. You wouldn't want that to be with a cable arcing and sparking wherever it's touching. Now you translate that into a piece of switchgear or a transformer, then there's the potential to do a huge amount of damage. Switchgear can potentially get thrown around. The coils inside the transformer will try and twist, and obviously if they break free with inside the tank, then you're going to get catastrophic failures inside the transformer tank, which could ultimately lead to something a little bit more seriously. And this is the kind of effects post faults that you may see on either switchgear or the transformer there, which is caught fire. Both are going to be incredibly expensive to replace and time consuming. One thing you find with switchgear and transformers, it's not held in stock. Unlike LV devices, which you can go there, you can phone up the local distributor and get a replacement breaker. With HV switchgear, it is always made to order. Transformers, at a certain size, you may find them in stock, but above a certain size, they are going to be made to order. Now, some companies will take precautions and keep critical things in stock. So the National Grid, who run our transmission network here in the UK, they actually keep very large transformers in stock just in case they have a catastrophic failure. So they can have downtime for maybe 2 or 3 days whilst they get the new transformer out of stock, up onto site, and then installed and then commissioned, and then that bit is then restored. So that's something that we hopefully we're going to prevent. We can't always prevent it from occurring. Another catastrophic occurrence can be life-changing or even life-threatening to maintenance engineers, and the photograph on the right is highlighting the poor old engineer. He's actually caught in a shower of sparks, and whatever was going on there, I have literally no idea. Now, one of the things that you need to be mindful of is, A, what are you protecting? What do you want to safeguard? What do you want to minimize? And above all, is there going to be any risk to personnel? And hopefully the protection or the protection chain going upwards is going to work. Now with HV protection, we don't want it to be tripping every day, every week, or every month. Quite often, HV protection is going to be sitting there in the background, just watching and waiting for something untoward to occur. And another term I've heard about protection relays, they are the silent sentinels. They are sat there waiting for something to happen. And it could literally be for 2 or 3 years before they're actually brought into life, which will bring into the factor that the rest of it, and you'll see in a few slides time, how important it is to have the circuit breaker as part of your maintenance schedule. So if you don't maintain the circuit breaker, it may actually stick when the protection relay has actually told it to do something and it hasn't done. So therefore, the next one above should work. So it's got to be capable of working even after it's been installed after a long period of time. Okay, so what are the concepts of protection? Well, we've got other actors in play here. So the right-hand picture there is showing a cross-sectional view of what we call withdrawable switchgear. There are 2 types of switchgear. You've got fixed pattern switchgear, which the circuit breaker is in circuit all the time, or you've got the withdrawable circuit breaker, so you can actually mechanically rack the breaker out of the circuit. The choice of whether it's going to be one or the other is entirely down to the technical specification and ultimately the end user's choice or the consultant's choice. But the key concepts here is we have got the circuit breaker, which is the brawn. It's the dumbest thing on earth until something tells it to do. The thing that's going to tell it to do is the brains. So if we're thinking of a human body here, so what we've got is the human body represented by our shadow. So we've got the brain, we've got the brawn, we've got the brawn, and we've got the sensors. Now the sensors come in the form of current transformers or voltage transformers, simplifying them, CTs or VTs. That's gathering information in real time. All these are doing is giving a accurate mirror image of what's happening in the circuit. Instruments like relays and meters do not like high voltages, do not like high currents, so therefore we need to step it down. And CTs and VTs are the accepted way of doing that. There are other things called LPCTs and LPVTs, which stands for low power current transformer, low power voltage transformer. They're working in a slightly different way to the standard CTs and VTs. So we get the information, the brain will think, and then it will tell the circuit breaker to act. And there is that protection chain. Now, our protection relay is doing more than that. So it might have logic within there. It might have to communicate onto a communications network via SCADA. It might store information. It might send alarms out. So the alarm is going to be there. Something is getting close to its critical point, i.e., if you don't do something about it, then I'm going to do something and trip the circuit breaker. So that's going on all in our protection relay or protection relays. And the reason I say protection relays, quite often end users want more than one protection relay for one reason or another. Now, when we start to look at what's going in and going out, we've got a mix of analog information and digital signals. Now, the analog is obviously current and volts and frequency and speed. We do look at speed on protecting motors, but for normal circuits for feeding transformers and cables, we're going to be looking at currents, volts, and amps. And that's where the brain will start to do the calculations. Once you get current and voltage, you can start to calculate all sorts of things. So you can look at your power factor, the energy, harmonics, thermals, etc. You can even calculate thermal rise of a transformer just by current and voltage. Ideally, it's ideal to get additional temperature inputs as well. And then you may have inputs from other sources like the status of the circuit breaker. Is it closed or open or closed? Are we in local or remote? Do we need an external trip or not? And can we reset it remotely? And there's going to be a whole host of others as well. So you ask, you can get. And ultimately, you can either do that in a local environment or you can do it via SCADA. And this is where IEC61850 will start to come along. You can even use the protection relay to check on the health of the circuit breaker by monitoring how many times it's operated, how much fault current it's actually interrupted, and how long it's taking to, the circuit breaker is taking to open. All that information is going to be readily available in the modern protection relays, which are now on the market. But more on that in a minute. So what's the concept of this protection chain within inside the cubicle? Now, the difference with high voltage and low voltage is where the protection is based. So with low voltage, generally we'll find the protection that it forms part and is embedded within the circuit breaker. With high voltage, you'll find that the protection relay is going to be in its own cabinet or cubicle on top or at the bottom of the switchgear. On the really high voltages like the national grid, they will have a room dedicated for protection relays, and all the information is coming in from the circuit breakers, and these circuit breakers are huge. You're talking tens of meters tall in some cases on the really high voltages, and it's not a room that you would want to be in if it trips. So anyway, let's work through how the whole thing works. So circuit breaker, we're going to close that, we'll get a healthy circuit, and everything is sitting there quite happily for as long as it is until, and I refer to it as the big yellow cable finding machine, and that's your JCB. They are yellow, they have JCB all over them, and they are very good at finding cables when they're digging holes. So we chop through the cable, fault current will flow to the point of the fault, will not go beyond that, and the sensor is picking it up. Now, within the protection relay, we've basically got a table of information which the you may have actually worked out what that is, and all the relays comparing against what's coming in, what is already there, and then it's going to decide when and what needs to be done. So it may be done what we call instantaneously, or it may be done after a period of time. I'll discuss that in a few slides' time. So at the end of the day, it's not going to predict when that fault's going to occur. We haven't got there yet, but it will limit the consequences. It's exactly the same scenario as when you're driving your car. You can't predict if somebody's going to walk in front of you as you are driving down the street at whatever speed that's going to be, 10, 20, 30 kilometers or miles an hour. But the brakes and your brain and the speed of your reactions will help limit either the damage or the shock to that person walking in front of you. So that's how I liken a protection relay to everyday life. Now, let's start to break down what we've got for the different types of applications. And some countries will still use HV fuses for protecting distribution transformers. These are distribution transformers which are going to be around about 800 to 1000 kVA in size. Here in the UK, we've moved away from that technology to circuit breakers and protection relays, or something similar to protection relays, and that's what I'm going to cover on to secondary distribution. Now, secondary distribution and primary distribution, it's still the same voltage, so it could be 11 kV coming in and 11 kV going out onto the network. So we're not differentiating on voltage. What we are differentiating on is the type of equipment. So liken it to your connection to the grid, i.e. your utility, or here in the UK, we refer to the utilities as distribution network operators. So the first point of connection is going to be what we will class as the primary distribution board. And then out on the network, whatever network that's going to be, we will class as the secondary distribution. Now, the most popular distribution network that I've come across is what's called an open ring. And an open ring, we're going to be using ring main units, and that's where our simple protection is required, because quite often that ring main unit is going to be in a substation without an auxiliary supply. So the protection relay has got to work by itself and powered purely from the CTs within the ring main unit. Now, here in the UK, we have got two forms of protection that we can use on the ring main unit. One of them is called time limit fuse, as it says there, goes back to the 70s. And instead of being a protection relay in its traditional form, we're actually using an LV fuse, which is in parallel with the trip coil. And there are going to be the potential for three. So two of them will be overcurrent, and the third one is going to be potentially for earth fault. Now, some end users will actually use all three because it's a way of finding out what you've tripped on. So if you've had an earth fault without an earth fault fuse, you're not going to know whether it's an overcurrent spurious tripping or whether it's going to be an earth fault. So if the fuse has popped, then that's an easy way of identifying whether it's an overcurrent or an earth fault. And the schematic that we've got there on the screen is very, very simple. It works quite simply in the principle that if the CT secondary current, i.e. that's coming down from these legs here, exceeds the fuse size here, then the current flow has got only one way to go, and that's through the trip coil, which I've just drawn a circle there. So by current flowing through the trip coil means the trip coil is energized, and then it will trip all three phases. The reason current will only flow through the fuse and not through the trip coil is because the fuse has got a very low impedance, whereas the trip coil has got a very high impedance. And the photograph on the right is from one that's on the production in Leeds. Now, we don't, as a manufacturer, we don't supply the fuses because we don't know what transformer it's going to be protecting. So we would leave that choice down to the consultant or the protection engineer. And the CTs that we would fit will be dual ratio CTs. So there is flexibility with this, but there isn't a great deal of flexibility in altering the time grading on them. You literally have got what you've got with the curve that is it, which is natural within the fuse. And this table here is agreed and signed off by the Energy Networks Association. So this is the body which the utilities in the UK are all members of, and they agree a whole heap of different technical specifications and sign up to them, and this is just one of them. So if you want to delve into it a bit more, get onto the ENA website, and you've got to buy the technical specification 12.6. They are free. They're not free, but you have to pay for them, and it will give you a lot more background to it. So this is the table from there, and at the end of the day, it's down to your decision as to which fuse you're wanting to use on the high voltage side, and that will give you the recommended grading on the low voltage. Now, this is only good for when you've got the fuse on the LV board as the primary incoming fuse, not an air circuit breaker or a circuit breaker. The coordination is going to be a little bit more complicated and difficult using this protection on the HV when you've got the circuit breaker on the LV. So benefits and disadvantages. It is very simple. It is very, very good on clearing faults. The disadvantages there, your fuses are fixed. You can't go intermediate. You can't go above what the table recommends, because you will not be able to get, well, you might be able to get a fuse, but the RMU manufacturer, ring main unit manufacturer, will not be able to fit the CTs in the CT box in the protection in the equipment. So moving on to one which is common throughout the world, and it's a relay called the VIP 300. This is truly self-powered. It does give you that flexibility on your protection curves, and I'm going to come on to that one in a couple of slides' time. It does give you your time delay as well, and it does give you indication of what you've tripped on. Now, that one is now obsolete, as it says there on the slide. Moved on to this one, it's giving you a little bit more benefits over the previous one, where you can see what load you've got on your circuit. You've got more flexibility. You can set it down to an amp, and you can actually do what we call sensitive earth faults. So anything that you need below, say, 2 amps earth fault protection, then you're going to need to use what's called sensitive earth fault protection, and I'll cover that in another slide as well. So moving on to primary distribution protection. This is where the relays start to become the more complex protection needs. Now, if we look at the historical path of protection relays, now there is a correlation between the first transformer going into service and the first relay manufacturing plant going live, i.e. commissioned. And that date is quite significant. 1886, when the first transformer was put into service, and when the first relay plant was operational. And they were on different continents. So the transformer went into service in America, I believe, and the relay plant was in France, Paris to be precise. So relays have come a long way since 1886. There are still a lot of electromechanical relays in service today. And then the next generation was solid state. So we've got the solid state one there. And then we're into modern relays, which are microprocessors. So we've got computer chips in there. So there's going to be more power in one of these protection relays, modern protection relays, processing power than the computers that put Apollo 11 on the moon. And that is just an indication as to how far we've come with the technology within protection relays, and everything in our own lives as well. Mobile phones is just one of them. Now, when I talk about server or mainframe, this is moving away from actual protection relays, which are dedicated in the circuit breaker. It's going to be a PC or a server which will do all that work for you. When you think about it, what's going on inside the protection relay on the bottom right, it is a computer. So you're just transferring the computer program into a PC with a screen, and then everything is then done digitally, from the sensors through to the telling the circuit breaker what to do. And that will be the next big move forward, I predict, within protection. And that's been around for quite a while. So anybody who's familiar with the utilities and DNOs and overhead lines, you've got a circuit breaker on a pole at the top, connected by an umbilical to a box. Inside the box, you've got a remote terminal unit and a protection relay all combined, and it doesn't look like a protection relay. So that's been around for quite a while. So it is nothing new, but as far as primary distribution is concerned in the large substations, that will be the next move forward. So this is just a timeline for Schneider, and Schneider is no different to the likes of ABB, Siemens, etc. They've acquired companies along the way and will continue to do so for the foreseeable future. The reason you acquire companies is A, to acquire technology, B, to acquire expertise, or C, to fill a gap in the market. And it does take time and a lot of expense developing your own products. So it can be a quicker way of actually getting into new technology. And Schneider is no different in the protection relays. So the top one is a brand called CPAM. They were actually developed by Schneider. Then Schneider acquired Arriva D. And what Arriva T&D did, they can trace that history back to the company called GEC, which was a ginormous engineering conglomerate, and they did all sorts of stuff, mechanical and electrical engineering. They had a range called MyCom. Now, MyCom is a collection of companies. So the MyCom P20 series is one company, the 30 series is another company, and the 40 series actually happens to be a development that Arriva T&D did. VAMP is another company which was acquired by Arriva T&D, which then came into the Schneider family. And whilst the relays do very similar things, some relays will do some things that others won't do, and that's exactly what VAMP does. It does things called arc flash detection and protection. So let's look at mechanical relays, and that's what they look like. They are big. And like our time limit fuse, you need 3 to do overcurrent and earth fault. When we talk big, we're talking about maybe 0.5 meter for all 3, and they come as a block of 3. So that's overcurrent and earth fault. So if you wanted frequency protection, you'd have another one. If you wanted under or over voltage, that will be another one. And so on and so on and so on, until your poor old LV cabinet became full. And that then led to the rise of relay cabinets, which will be either wall mounted or put into a separate room. Now, compress all that into one box, and that's what you get with the modern protection relays. Unfortunately, these relays do need some maintenance, and they have springs in there, they have contacts in there, and one engineer told me that you get a goose feather as part of your maintenance kit to clean the contacts with dust, and if you accidentally knock one of the springs off and you don't realize it, then the relay isn't going to work as it says it is. So ignore all the complicated lines. Quite simply, we have current coming in from our CT, that's there. We've got, that's going to drive a coil, which is then going to drive this disc, which has got a peg on it. And then there are 2 contacts. So that is an open circuit for the trip coil for the circuit breaker. Now, with circuit breakers, you will always have stored energy in the form of springs. That's typical what you would find in a circuit breaker, is springs, very powerful springs. And when a circuit breaker closes or opens, the bang that you hear is the spring energy being dissipated. So the peg, which is conductive, basically, if it short circuits this, is actually going to operate the trip coil. So we need a supply, a DC supply, and somewhere this is now leading to auxiliary power. So we can set our disk at 1, so it's going to be at that point there. And depending on the current from the CT secondary will determine where this peg is going to go. So if it's at its set, if the current is below what we call its set point, that peg ain't going to move. But as soon as we hit the set point, this peg is going to start to move towards the contacts. Now, depending on how high the current is above the set point, so a set point is the current setting you would set on your protection relay for it to trip. Now, it's not going to trip straight away. Well, it may do. It depends on the what curve you chose. But in this example here, this peg would start to move at either a high speed or a slow speed, depending on the level of the current. So the higher the current, the quicker the time it's going to take to send a trip signal to the circuit breaker. Now, down here we've got this time multiplier. So if we now change it to 0.6, for instance, we're actually physically moving our peg to somewhere here. So instantly, the peg hasn't got as far to travel as it did before. So that's how a time multiplier works. It will either move the time it's going to take either faster or slower, dependent on your application. So that's how an electromechanical relay will work. Now, if you want to delve more into it, then obviously Wikipedia and Google will be able to give you a lot more information than I've passed over today. But that's the basic principle of a mechanical relay and the introduction to time curves. Now, moving on to our modern protection relays. Well, they are a computer, as I've already said. They've got a processor inside there. They're able to do complex multiple calculations at several times. You are getting metering in there, but be mindful that it is not tariff class accuracy, because you are working off of protection CTs, and at best you're going to be getting 5% accurate on the CT. So just be mindful of that one, but you can get it will give you a guide as to what you've got, and you can actually do power factor analysis, etc., all from that one protection relay. Now, I've talked about connection onto SCADA and communications, but this type of relay here has got the ability for what we call near field communications. And it's using an app on your mobile phone, and you scan a QR code on the relay, and provided the phone is whitelisted with the relay and you're registered, obviously, for your cybersecurity issues, then you're able to see what's happening with the relay in a safer environment, i.e. outside the substation, but you've got to enter the substation to be able to scan the QR code. So within a certain distance, you're going to be able to get information into your mobile, and potentially, if you've got the authority, to operate the circuit breaker using your mobile phone without having to go through SCADA. But obviously, I appreciate that some of you will be thinking, I don't really like that because of the potential for anybody to hack into it. These things, like a lot of things in life, you can actually disable them, and whitelisting your mobile phone or whatever onto the relay is one of them. So that's the kind of technology which is available today, and replacement of relays very, very quickly is also the technology of today as well. And when we talk about fault diagnosis, we might need to know what's been going on in the fault. during the fault and after the fault, and that's called a disturbance recorder, which is becoming more and more standard within relays, and it will create what's called a contrad file, and you can download that file, and it gives you all the waveforms, and you can see what's been going on with each phase and such like at your leisure if you're trying to work out what's going on. Now, with the advent of color LEDs and color displays, that technology is now with us for protection relays, and you can program your LEDs to do whatever you want. Solid color, blinking color, different colors, you name it, you can do it. Okay, so now we're going to look at curves, and there are different curve shapes depending on what you want to do. There are going to be different curves depending on which area you are in. So North America, for instance, has got different curves to IEC. Russia will have different curves for their country, same with China as well. But the curves I'm showing you here now are the inverse curves that we would see typically in IEC. So if you really want to know where they come from, IEC61850 is, these are just the three that we see on a very regular basis: standard, very, or extremely inverse. Now, there are two others which I'm going to discuss. Now, these work on a log scale, both on current and time. So your bottom axis is time, the vertical axis is current. Now, depending on which curve you've got, so if we take, for instance, draw a vertical line down the 10 one there. So a very accurate line there. So on the very extremely inverse one, it's less than 1. When we get to the, so that's the extremely inverse. When we go to the very inverse, we're just above 1. And then when we move on to the standard inverse, we're at 2, just above 2. So dependent on your curve, dependent on your time delay, will determine where that is going to pick up and what time delay is going to be applied before a trip signal is sent to the circuit breaker. Now, one thing that you need to take into account is the mechanical operating time of the circuit breaker, which is going to be 55 milliseconds for HV breakers. Other things that you need to take into account is safety margin. So typically between protection relays on the same circuit, and I'll touch on this when I get to my worked example, you need to apply typically 250 milliseconds between protection relays if they are the modern type, and if it's between mechanical to mechanical or modern to mechanical, is going to be an increase of 350 to up to 350 milliseconds. So that's just as a general guidance that I've got from our a consultant that I know. So when we talk about pickup time, it's the start point of the curve. So that one there that I'm just drawing down now will be our pickup point, and it's at the start of the curve. So the higher the current, the quicker it's going to take the trip signal for it to send a trip signal. And it is a trip signal, so it's telling the trip coil to release the energy in the springs, and that will then drive the mechanical movement of the contacts inside the switchgear. And that will, the actual contact opening is going to be 55 milliseconds. And what's happening inside that between those contacts is a lot of energy, particularly under fault conditions. So what you don't appreciate, you're striking an arc inside that tank, and it's how you dissipate that arc between the contacts is key to it interrupting the circuit within the time you want. Okay, so that's inverse curves. Now, there are two others I've already mentioned. One is definite time. So this is the shape of the curve. So we put a set point there, and then we put a time delay on it. So as soon as we hit the set point or exceed it, it's going to be a constant time, irrespective of what the current is going to be. So that's typically what you might find in your mix of curves. Another one is instantaneous. Now this is got noted out time delay on it, as you can see. So as soon as you hit or exceed the set point, it will send an instant signal to the trip coil, and then 55 milliseconds later, you've got a fully open circuit. Now that could be used for whatever reason you want to do. So you may not want, when you get to a very high current, say 2 kA current, you may want it to have an instant trip. But below that, you'd be quite happy to use it on either a definite time or a time delay curve. And one of the applications that may have come across on this Instantaneous is what's called live line working, or hot glove, on the with the utilities on their overhead lines. So classically, they will install a pole mounted transformer with the overhead lines live, and you have a hot glove team, two hot glove teams. They work in pairs. They're in insulator buckets, so by and large, they're insulated from the ground. But what you don't want is if they cause a fault on the overhead line, you don't want the recloser to go through its cycle of trip, close, trip, close, trip, close. So one of the functions within the control cubicle of the recloser is live line or hot glove working. So that does two things. One, it disables the auto reclose cycle, and B, will lower the protection settings to probably its bare minimum, and then it may go to instantaneous, but that would be for the planners to decide. But that's the kind of application that you can see where it's going to be used in that kind of application. Okay, so combining the curves, you may see something like this. So we've got an inverse curve with a definite time curve with an instantaneous. And that will get you through all sorts of problems. Now, I can't advise one way or the other what curves you're going to be using. I can only show you some examples, and I've got a couple of examples now to show you on time grading. One thing I didn't talk about, again, another difference between high voltage and low voltage is we grade by time. We don't grade by current. So you can literally have all your circuit breakers on a network, exactly the same current rating, but then you would grade them by time. So the one on the incoming would be one time, and then as the further down the network, the quicker the time is going to be coming. So you could end up being a problem. Now, I do have a trick up my sleeve to get around that, but I'll come on to that one at the appropriate point. So here we've got a very simple single line diagram of a hospital network. So it's got an incomer there from the local utility. This is an old name for a network which is part of UK Power Networks. They've got 3 networks. They're licensed for 3 networks, and Seaboard was the southern end of their network. So this is down in Kent. So that's off a ring main unit, which is here. So that's a ring main unit being fed by a circuit breaker onto the first of the 3 incomers that we've got. So we've got 3 generators that are connected onto this switchboard. So we've got 3 high voltage generators and 1 low voltage generator. At this point in time, it's worth pointing out that high voltage generators are a potential source of a fault. So when you're doing network calculations, besides time grading, another factor you need to take into account is fault calculations as well. So generators can have a significant impact on the fault level of the switchboard in this case here. So that's just another factor that you need to consider, especially when you get involved in adding generators onto an existing switchboard. You need to do your fault calculations. Anyway, moving on from that. So we've got our Seaboard supply coming in. So that's our A is our first circuit breaker. We've got 2 bus sections, but I'm going to actually ignore those because they are closed, and it's not an indication as to what protection there is. We've then got 3 substations, so number 1, number 2, number 3, with ring main units inside them. So the way I'm approaching this, and it may not be the right way, but it's the way I always approach it, is to look at things in isolation. So we are going to consider this bit. So we're going to ignore that, go around that, come around here, over here, and back to here. So we are going to be looking at the supply from Seaboard, our incomer. Sorry, I've missed that one there. So we need to consider F as well, and then our ring main unit feeding our transformer, and then the first 2 on the LV side as well. So that's what I'm going to look at in the next slide. Okay, so programs like Amtech will give you the time grading or the discrimination study that you need to get everything in the correct order. So we've got our C-board, so that's our supply circuit breaker coming onto our incomer A. So looking at the curves here, these are what have been set. So the utility incomer, the utility curve is using a standard inverse curve, and that's fixed. That's the thing you have to work from. So moving on to our incomer, which we've got here, we're now on to our very inverse curve. This is what the consultant has chosen during this study. Moving on to our ring feeder there, you'll notice there we're following the same curve, but the actual safety margin between the 2 curves is quite small. And when you compare your incomer A against your C-board, there is quite a good safety margin there. Now, the reason they've closed the gap between those 2, because the incomer is feeding that, if the incomer A goes out, you're going to take out that half of it, you're going to take out part of the ring. Sorry, if ring feeder F trips, you're going to take out half the ring. If the incomer A goes out, you're going to likely take out the whole ring. So the actual impact is not going to be as great as if that one tripped, the C-board one tripped. So moving on to our next one. So this is our ring main unit with a VIP300 relay. See, there's quite a good safety margin between those 2 curves there, and it's very inverse again. And that is using 2 curves. So we've got a combination of an inverse curve with a definite time curve. So that's why we've got that dog leg in there. Now the VIP300 has only got the capability of combining 2 curves together. Modern protection relays will have the capability for going 2, 3, 4, or even 5 set points. So combining 5 curves. So it depends on what relay you've got, will depend as to how many curves you can actually combine. So in this case, we've only got 2. Now, moving on to the LV side of it. So our 2,500 amp device is on this curve here. And you notice there it's crossing over the ring main unit circuit breaker curve. So that's a consideration you need to take into account. Now, this LV, if this one trips, it may mean that there's been a short circuit on the bus bars, which is something which is going to cause a lot of problems. So taking out the HV isn't going to be a great thing, a great factor that you would need to worry about commercially and technically. Commercially, that's one consideration. Technically, there's got to be another consideration. And you notice the next LV device is well clear of our protection, HV protection. Now, another thing that would need to be taken into account is what's called transformer inrush. Now, all transformers, irrespective of their size, have a transformer inrush curve, and I'm getting mindful of the time now, so I'll try and speed up. So when you switch a transformer on from cold, you're energizing the core, so therefore you get a very high inrush of current, anything between 10 and 20 times your normal full load current. That will be for a period of time, and then it will drop off. So you need to be mindful of where your inrush current is going to be, otherwise you could end up with nuisance stripping. Now, these are just two examples of curves. So the red curve is the high voltage using time limit fuse. I said there's not much flexibility with time limit fuse. You can see there, the green and the blue are crossing over, which is probably going to be a problem. But by moving on to a VIP 300 protection relay, we've managed to get plenty safety margin in there between the orange, green, and blue. So orange is HV, blue and green are LV. So that's good time grading in my eyes. Now, I did talk about how you can get around it, and this is called blocking on blocking schemes. It's using the logic within the relay to send a blocking signal to the relay above it to not trip. And you can have all your time grading exactly the same, and that gets you around some of the more ticklish problems that you may find. Now, so additional things that you can include with transformers is Buchholz, and we call it a Buchholz relay. It's basically a big block which will pick up faults inside the transformer that the protection relay may not do. And there are other techniques you can use for advanced transformer protection, which I'm not covering today. So what it is, it's a big block, and it needs a pipe from the transformer tank up to a head tank called the conservator. And basically you've got two contacts in there. One is for alarm, one is for trip, and dependent on the condition of the transformer, dependent on the fault inside the transformer, you're either going to get an alarm or you're going to get a trip. Now, what you can use this for is low oil as well. So if the oil starts to leak from the transformer, it will sink below the trip contact, and hey presto, you've got protection of your transformer that way as well. So moving on to the very last slides now, ANSI codes. These are recognized numbers, and you will see them as numbers on schematics, maybe against the circuit breaker. If you Google it, there are ones which will cover loads of different things, mechanical as well as electrical. It's been going since 1927 and is an American system, but it's very well recognized throughout the world. And when we talk about protection codes, there are a whole heap of different ones. Now, these are the common ones. So overcurrents and earth fault, those are the two common ones that you're going to come across day in, day out. But then when you talk about restricted earth fault, this can be used for advanced transformer protection, or you would find restricted earth fault on LV as well. Pilot wire or differential protection, that's just looking at a lump of cable on between two circuit breakers. Directional protection is going to be something quite sophisticated, where you're potentially going to have fault current flowing in the opposite direction. And when we talk about differential protection, this is transformers. If you think about a transformer sitting there, what goes in generally goes out. But if you start to get an imbalance inside the transformer, that's another way of advanced transformer protection, etc., etc., etc. Now, just looking at what we've got here, this is just showing you how we can do sensitive earth fault protection. So when you need to get down really low currents, i.e. down to 0.2 of an amp, you need a 4CT, which will go, that 4CT will go around all three cores of the cable. Moving on, where's Schneider going? Well, like cars, like the VAG group, you want a common platform, and this is exactly what we're doing with the protection relays. So everything will be on what's one common platform with one common software for programming. And these are just some of the relays that we have brought out recently. Instead of having dedicated relays for specific functions, we've got a universal relay. So you pick the function, you pick the application when you're programming it. So it helps with simplicity, or you can have actually dedicated ones if you need to. So on the last minute or so, IEC61850. It's a vast subject, and my 2 slides or 3 slides not really going to do it justice. Now, there are webinars, seminars, etc., which cover this in a lot more depth. And basically, IEC61850 is trying to harmonize things. Now, harmonizing things is going to be quite difficult. Now, if you take a traditional large substation and you've got comms on there, the traditional route is to choose what protocol you want, and then you select what supplier you want, and it might be multiple suppliers of meters, relays, etc. Now, getting all those to work together can be actually very, very time consuming, and this is where IEC 61850 comes in. So if you picture that in your mind, you've got a choice of your protocol and you've got a choice of devices, and getting the two different manufacturers' devices to talk to one another can be the most problematic thing on earth. Plotting fog might be easier. Okay, so where's it all sprung from? Well, it's an IEC standard. So it's not a protocol, it's a standard. And it's basically there to help you with the design and configuration of an electrical substation. And we call it automation. It's been around for quite a while now. And the International Electrical Technical Commission is the body. Okie doke. It's become the cornerstone and was first voted in 2003, as it says there. We're now on edition 2, so you may be working on edition 2, or you may, equally it may be edition 1. The whole promise of this is that it's interoperability between different manufacturers. So if you've got a device which is IE61850 compliant, provided you've got the right engineering tools, the whole thing will work. Now, it does sound very, very simple, does that? But translating it into this slide here, and this is my last slide, you can replicate projects. So if you are designing data centers, for instance, and you're creating a data center model that is going to be replicated throughout the world by using IEC 61850, you do all the hard work with the first model using the right engineering tools, and the engineering tools across manufacturer. So you have various different codes which IEC 61850 will come into, and you just then design it, take the single line diagram, design your thing using your engineering tools, and then that will write the appropriate programs, and then you basically squirt that into your devices, and hey presto, it should all talk together, and you're using fast Ethernet bus. So if you hear somebody saying, well, we need ghost messages for this, it's not the honk honk feathery variety, it is actually IEC 61850. That is the end of the session, and I apologize for taking 3 minutes longer. And Andrew, I believe you've got some questions on the chat. So if you'd like to sift out 2 or 3, and I'll have a go at answering them.
Yeah, what we'll do, I'm conscious of time, so what we'll do is we'll just pick a couple of questions from the chat. I don't know if you can see these, Nick. If you just open that up at the bottom, you might be able to read them as well.
Right. Which is it going to be under Q&A, or is it under?
Just click on the Q&A and you should see them in there. What I'll do, I'll just before we start, what I think I'll do is I'll copy all the questions into a Word document, and then I'll forward them over to you, Nick. And then if you would be so good as to just put an answer under each question, and then what I'll do is I'll put the Word document or the PDF with the answers on it on the IET Humber sites under the files tab. So I'll do that at the end, but we'll just pick up maybe 1 question or 2 if we've got time, just to make sure. So the first, do you want to, you can see the first question. Just I
can see the first question. Right. So Mohammed, it's going into right. So how on earth is earth current sensing in the time limit fuse I think it was on slide page 16. It probably was. Grids are now introducing power electronics, VFDs, which introduce harmonics. So the way that very simple time limit fuse works, you're working on instantaneous at either 25 amps or 30 amps if you haven't got a fuse. So it's with time limit fuse, you can't. It's not going to detect what harmonics you've got in there, if that's a way of describing it. I know the harmonics are going to be fed back up into the system, and it's something that time limit fuse will not actually protect you against, is harmonics. So if you know you've got something, if you know you've got a problem with harmonics, A, you need to measure it and do something about it if you can. And B, you would need to go to something a little bit more sophisticated, which is going to pick up and protect on harmonics. On the next generation of protection relays for distribution substations, i.e. your distribution transformers, you can do second harmonic restraint. So it's actually blocking the second harmonic when you're switching the transformer on. Okay, second question, can you please describe a bit more on data output formats? Is the data output format of relays unified across all manufacturers? Let's put it this way, no. There's a simple answer. The information that you get out of a protection relay, the event logs, etc., are going to be event logs, so that's going to be specific to the relay manufacturer. The actual comms, if that's what it's, if this question is referring to, is going to be whatever protocol it is. So it's all about your mapping. Right. So quickly moving on, and this is one I can answer. No, we didn't take all the GEC relay protections. So when we acquired Arriva D, another company that was part of that acquisition was Alstom, which is now GE, and it was split. So Schneider took the protection relays for distribution. We didn't take the electromechanical relays. So if there is any electromechanical GEC relays, then I would talk to GE, and they are based down in Stafford. Is there a comparison for railway overheads and very inverse? Now, railway protection is quite specific, and you will get very specific relays for railway applications, because the catenary, the loads are very, very variable on the catenary, and so railway protection is quite sophisticated. Right, the fault levels are reducing in the networks due to displacement of conventional generation. What solution interested for reliability of current-based protection systems for 100% or near 100% renewable base generation? Wow, right, that's a challenge, because when you say fault levels are reducing in the networks, it depends on who you talk to on the DNOs, because the DNOs do experience grid substations tripping because of the contribution of power from renewables. So WPD have had issues in the past on solar farms tripping the grid substation. So it is a problem for the DNOs. Now, as far as your private sites go, if you've got your own renewables on that site, then you're going to have to design your protection accordingly. So you're going to have to possibly look at directional protection as well as everything else. So I know it's not probably a very good answer for that one, but I hope it gives you an idea as the thing. Right, so Alan, do Schneider have assistive software for fault level modeling and protection settings? Yes, we do. It's a company that Schneider has recently acquired, so I can't remember the name. So we do have a company that do that kind of stuff, and it's quite extensive stuff. So I will try and send a link to Andrew when we're finished, once I've had some lunch. So I'll call this one the last one. Mohammed, DC is making its comeback, so please let us know if there would be a webinar on DC protection and consider it to be taken. Quite simply, I can't answer. I can't do any DC protection because Schneider's expertise and our main area of business is AC. So DC is quite a complex subject, and breaking DC is quite a complex subject, and it's something I have no answer on that one, I'm afraid. So grading studies, the very last one. What is a standard discrimination term for each breaker voltage level? Right, so, and how do you decide which is correct? Well, obviously you need to do a grading study. I did give an indication between sort of the time, the safety factor between breakers, 250 milliseconds, for instance, between your modern relays, and 350 milliseconds between a modern relay and a mechanical relay. That's the kind of general thing. But it's doing your protection study is key to getting the grading right. Okay, Andrew, I think we'll call it a day on the questions there. And if you ping them, or if you copy them all onto a Word document, and then I'll answer them over the next week or so.
Thank you very much, Nick. That's a very thorough presentation. We do appreciate that. And say excellent slides and excellent content. So thank you. What I'll do with the questions, I think you nearly got through them all anyway, but I'll put them on a Word document, and then you can have a think and put any details and links as an answer to those questions. Yep. And then what I'll do, I'll copy or save that document into the files section of our IET Humber website. Okay. So I would like to say thank you very much. Very thorough presentation. So much appreciated. What we'll do, we'll end the session there. So thank you for joining, and appreciate all the comments in the chats. So thank you for all the information and the comments, and also the questions. Regarding the next events, if you keep an eye on the IET Humber website, and also the LinkedIn pages, which I think Paul's put a link to in the chat, you'll see all the upcoming lectures. In the near future, they'll all be online, obviously, but later in the year, all being well, we'll be back and doing some face-to-face meetings. So thanks again, all, and enjoy the rest of your day.
Yeah, thank you very much indeed.
Okay, thanks again, Nick. I'll send you the Word document over on email, and then if you wouldn't mind answering the questions, I'll post them on the website.
Yeah, certainly will. How many did we have? What was the top number?
I think it's around
216. I counted.
Yeah, 216, 219. I think at one point. So that's really good.
Are you happy with the numbers that turned up?
Oh, very good. Very very happy. So that's really good.
Apologies to answer your question there, Andy, on the thing. I just nipped out of the room when you sent it.
I know. Yeah. So what we'll do, I'll send that over now, Nick. If you do, you have a few minutes this afternoon just to type some responses?
Yeah, I'll have a look. I'll have a look at it this afternoon. I'll get out of the next meeting at 2 o'clock. I need some lunch anyway.
Yeah, get some much deserved lunch, and also if you let me have the slides as well on a PDF, I'll put those on.
Yeah, you'll get that this afternoon. It's ready to go. So once I've had some lunch, and my voice is recovered.
Fantastic.
I've got another one lined up as well, Andy. I've got the week of the 10th of May.
Okay.
Got, the guy who can do the partial discharge.
Oh, that's good.
The partial discharge. He's available that week if we want to. He sent me through a bio and a synopsis, so I can I'll forward that on to you and we can look to get that. That's a lunchtime one as well. Mm-hmm. What he wants to do.
Okay. All right. I'll end the meeting there anyway, and then
we'll
talk later. Thank you very much.
All right. Okay, then. If you ever need me again, just give us a shout.
Will do. Thank you very much.
Okay.
Cheers.
Cheers.
Bye.
Bye.